In today's session, we are going to discuss about the unit current electricity. In this chapter, we will be discussing about the meaning of electric current and then resistance, resistivity, the factors on which the resistance of a conductor depends, the factors on which resistivity of a conductor depends, and the expression for resistivity, relation between resistivity, relaxation time, number density, mass of the electron, and the relation between current and drift velocity, so on and so forth. Let us begin the unit current electricity. Basically, we learn that the rate of flow of charges through a conductor is known as electric current. Let us look at a diagram. Here is a conductor whose length is L, whose cross-sectional area is A, which is connected to a source of electricity, battery, and it provides the necessary potential difference. When the potential difference is applied across the two ends of the conductor, say conductor having the two ends X and Y. When the potential difference is applied across the two ends of the conductor, there will be flow of charges through the conductor. These are electrons. The electrons move from negative terminal of the battery to the positive terminal of the battery. Whereas the direction of current is taken along the direction of positive charges. The direction of current is against the direction of motion of electrons. Basically, this flow of charges through a conductor is a skin effect. Only the mobile electrons will participate. Electricity is through free charges. Larger the cross-sectional area, it means larger the surface of the conductor, larger will be the flow of charges, larger will be the flow of electric current. So therefore, electric current is defined as the rate of flow of charges through a conductor. Where I is electric current, T is time, and Q is the charge. The electric current at a point is said to be 1 ampere if 1 coulomb of charge that passes through this point in 1 second. Fine. As we know that, according to Ohm's law, the current that is flowing through the conductor is directly proportional to the potential difference applied across the conductor. According to Ohm's law, the current flowing through the conductor is directly proportional to the potential difference applied across the conductor. So we write Ohm's law mathematically as V is proportional to I. The current carried through the conductor is directly proportional to potential difference. The potential difference applied is double. Then what happens to current? Current also gets double. If a PD applied is a triple, then current also gets triple. So as the potential difference applied across the conductor increases, the current flowing through the conductor also increases. That's Ohm's law. And the condition of Ohm's law is the temperature of the conductor should be kept constant. V is proportional to I is only for conductors at moderate temperature. At high temperature, Ohm's law does not hold good. That is one of the limitation of Ohm's law. Ohm's law is also not applicable for semiconductors and insulators. The substances which obey Ohm's law are known as ohmic conductors. For example, aluminium, copper, nickel, these are ohmic conductors. And the substances which do not obey Ohm's law are known as non-ohmic conductors. For example, germanium, silicon, rubber, they do not obey Ohm's law. Therefore, they are known as non-ohmic substances. Fine. So, according to Ohm's law, V is proportional to I, then V is equal to some proportionality constant into I, then R is equal to V by I. This is the another form of Ohm's law. We can also write I is equal to V upon R. These are three different forms of Ohm's law which can be easily remembered by using this technique. That is a triangular technique. Here is V, here is R, here is I. So V is equal to Ri, R equal to V by I equal to V by R. So what is R? R is the resistance of the conductor. Conductors have low resistances. Insulators have very high resistances. Semiconductors have moderate resistance. What is resistance? It is the opposition offered by the substance to the flow of charges. And this resistance depends on several factors. First, let me tell you how do we measure resistance. Resistance is measured in ohm in SI system. 1 ohm is equal to 1 volt divided by 1 ampere. 1 ohm is equal to 1 volt by 1 ampere. Volt is the SI unit of potential difference. Ampere is the SI unit of current. Ohm is the SI unit of resistance. Fine. Then let us discuss about the factors on which resistance of a conductor depends. As we learned in 10th class that as the length of the conductor increases, its resistance increases. So, resistance is directly proportional to length of the conductor. Resistance is inversely proportional to cross-sectional area of the conductor. As the cross-sectional area increases, the flow of charges, as the cross-sectional area increases, the flow of charges increases. Therefore, current increases because resistance decreases. I repeat, as the cross-sectional area increases, the surface area increases, the number of charges that are flowing through the conductor increases, current increases, but resistance decreases. So combining these two, resistance proportional to length and inversely proportional to cross-sectional area. So resistance is equal to some constant into L upon A. That constant is known as resistivity of the substance, which is Ra by A. Fine. Resistance not only depends on length and cross-sectional area, it also depends on two more factors. It depends on temperature and nature of the material. If the temperature of the conductor increases, its resistance increases. That is why at high temperature Ohm's law does not hold good. At high temperature V is not proportional to I. So totally resistance depends on four factors: length of the conductor, cross-sectional area, temperature and nature of the material. Nature of the material means if you take aluminium conductor, copper, then iron and all, having a same length and equal cross-sectional area, silver will have less resistance than the other conductors. It means that silver resistance is different, copper resistance is different, and then iron resistance is different. So resistance depends on the nature of the material. Well, what is resistivity? Resistivity does not depend on length and cross-sectional area. Resistivity depends on only the temperature and nature of the material. If the length of the conductor is double, resistance gets doubled, but resistivity remains same. As the temperature increases, resistivity increases, and resistivity is different from different conductors. Aluminium will have one resistivity, copper will have another resistivity, nickel will have another resistivity, silver will have another resistivity, and so on. But then how do we define resistivity? Suppose if you take a cube of any material having the unit cross-sectional area in unit length, in that case resistivity will be equal to resistance, because A is 1 and L is 1. Therefore, rho is equal to R. That means that the resistivity of this material, this may be a cube of aluminium, a cube of silver, or a cube of copper. The resistivity of this material is equal to resistance of this material when the material has unit dimensions, unit length and unit cross-sectional area. Then what is the SI unit of resistivity? From this formula, we can derive that SI unit. Resistance is in ohms, area is meter square, length is meter, meter square by meter get cancelled, meter. So ohm meter is the SI unit of resistivity. Fine. Now let us come back to what is the importance of resistivity? What is the importance of resistivity? See, in our homes, we use certain home appliances like electric heater, electric presser, electric kettle, electric stove. They are made of some alloys like nichrome, manganese, constantan. These are alloys. They are made of some metals. Mixture of metals is known as an alloy. This nichrome wire is used as a heating filament. This manganese wire is used as a heating filament. This constantan wire is used as a heating filament. Just like tungsten. Tungsten is not an alloy, but it is used in electric bulb because its melting point is very high. Similarly here, they too have high melting point. They have high resistivity. They do not oxidize at high temperature. Therefore, these alloys are preferred in making heating filaments. What is important of alloys? This nichrome, manganese, constantan, they do not oxidize at high temperature and their resistivity is higher than conductivity. Fine. Then, how do we define drift velocity? How do we define drift velocity? Look at this diagram. This is a conductor. It is connected to a source of electricity, battery. Okay. The direction of current is from positive to negative, and the direction of electric field, as we learned, that it is from positive charge to negative charge. So the direction of electric field is in the direction of current, because electric field always goes from positive to negative. And the potential difference is applied here. V is applied here between the points X and Y. Fine. When there is no potential difference applied across the conductor, then in the normal conductors, the mobile electrons will move randomly in different directions due to thermal agitation. At a room temperature, on the surface of conductor, the free electrons, the mobile charge carriers, move in different directions, random directions. Therefore, the net velocity of all the charges will be equal to 0. That we call it is initial velocity. It is 0 because the velocity of this electron get cancelled with this one, cancelled with this one, cancelled with this one. When the conductor is kept at ordinary temperature, the surface electrons will move in random direction. The net velocity of all the electrons becomes 0. Okay, suppose if the electric field is applied and all these electrons start moving in a particular direction, that is from negative terminal to positive terminal, electrons get attracted towards the positive terminal. Therefore, we define in Newton drift velocity. What is that drift velocity? It is the average velocity of the electrons when the potential difference is applied, when the electric field is applied. The average velocity of the electrons when the electric field is applied across the conductor. So, at this time, the electrons get accelerated. They get accelerated towards the positive terminal. They get sudden increase in their speed, velocity. So, V is equal to U plus AT. We take this equation. That equation of motion is applicable here also. Okay. What is this V? The final velocity of the electrons. The final velocity of the electron is called drift velocity. That is the velocity acquired by the electron after the application of electric field. When the electric field is applied, electrons, what velocity they gain, the average velocity they gain, that is called the drift velocity, which is equal to the initial velocity of the electrons. All electrons will become 0 because they get cancelled. Velocity of one electron get cancelled with the velocity of other electron when there is no electric field across the conductor. Plus, every electron gets accelerated, and this T is the relaxation time. What is relaxation time? The time taken between two successive collisions. How much time this electron takes to collide with this one, that is called relaxation time. Time taken between two successive collisions. I write it is tau. V is equal to A into tau. So, I write that Vd is equal to, what is acceleration? According to that Newton's second law of motion, acceleration is force by mass. In 9th class we studied F is equal to ma. M means mass here, mass of the electron. F means the electric force that is experienced by the electron when the electric field is applied. When the electric field is applied, every electron experiences electric force. So that force by mass is the acceleration produced in each electron into the relaxation time. So this force is electric force. That electric force is E into E into tau. In the first chapter we learned that electric field is defined as force experienced by each charge. Force per unit charge. This charge into electric field is force. So drift velocity is equal to E by m into tau. If you put here plus, that becomes the drift velocity of positive charge. If you put here minus, that becomes the drift velocity of electron. Fine. Now, if you want to write in vector form, you can write here drift velocity is equal to E into E divided by m into tau. This is in vector form, and you can write here negative sign. It indicates that the drift velocity and the electric field are opposite. This is the drift velocity of the electron. What is drift velocity? It's the average velocity of the electrons when the electric field is applied. These electrons, they drift towards the positive terminal. So drift velocity and the electric field are just opposite. Therefore, this negative sign. Fine. So you can write Vd is equal. Substituting this E as V by L. So we can write that EV by ml into tau. What is E here? E is equal to V by L. What is V? V is the potential difference that we applied here. What is L? L is the length of the conductor. The voltage that we applied across the conductor divided by the length of the conductor is equal to the electric field across the conductor. Fine. So this is the equation for drift velocity. Now let us derive the relation between drift velocity and electric current. What is the relation between drift velocity and electric current? Here is the electric current. Here is the drift velocity. What is the relation? As we learned that electric current is nothing but the rate of flow of charges. What is Q? Q is the total number of charges that are available here. How to calculate